Okay. So we talked about sampling distributions for proportion. Okay, and remember our proportion is like a fractional amount, or you can change it to percent, that somebody is in favor of something, for example. Okay, or if there's, you're doing by colors, a certain proportion is a certain color. There's all sorts of examples that we looked at. The other big question that you get are means. So we're going to talk about a sample distribution for a mean, and it's very similar to proportions, except there's slightly different formulas, and there's one of the conditions is a little different than the other one for a proportion. So as an example, we've got in the US, Veterans Affairs, which are for those people that have been involved in the US military in some capacity, and they have an accompanying health system, had very long wait times. So many veterans could not get appointments for months, especially mental health appointments, which are very prevalent when it comes to veterans for things like PTSD and depression. And you'll notice it says there these delays can be high stakes because there were so many, many veteran suicides that took place. And a big problem was they weren't getting the help that they needed, okay, because the wait times were taking too long. So government changed the leadership, and the VA, they said, no, we're going to speed up wait times. We got to improve on this. So our goal is to get a average 3-day wait time. So on average, a veteran would have to wait 3 days for mental health support. Okay. All right. Remember, we're going to talk right now. We're given information about the population. We're doing calculations about the sampling distribution. We're seeing the relationship because we're going to work the other way, because that's the way we normally work. All right, so if you remember the notation, mu represents the population mean. Which is a parameter. X bar represents the sample mean. It is therefore a statistic. And like P hat was for population proportion P, it is a good, X bar is a good estimator of the population mean. Okay, so we're going to do a lot of questions involving proportions, a lot of questions involving means. Make sure you understand the difference between the two, okay? Because sometimes it's easy to get them mixed up. And we'll talk about how do you recognize a mean question, how do you recognize a proportion question, which is pretty straightforward. Okay, so there was an activity, but in the interest of time, I've decided to skip it. Okay, where you guys would randomly locate a section in North America or in the United States, and then you would find the nearest town that had a VA office, and then find the average wait times. Okay, so that was to do something randomly. Anyway, so in this case, 30 clinics were randomly sampled. And the sample mean wait time was 5.33 days. So that should give you some initial thoughts, okay? The population mean, we want to be 3 days. The sample that was taken here was 5.33 days. Do you think they're meeting their goal? Doesn't sound like it. Can't be sure, but it doesn't sound like it. Okay, we need to do some math to follow it up. Okay, so what's the population? Well, yeah, you tell me, what's the population?
All veterans.
All veterans?
Well,
All VA clinics.
yes. That's all.
And the parameter is mean mental health wait time. And because it's population, because it's a parameter, it's mu. The sample is obviously, well, if the population is all VA clinics, the sample is the 30 clinics that were randomly selected. And again, it's the mean mental health wait time for the sample. So you may want to put population in front here and sample in front here, or you can just use the appropriate notation. Sample mean is X bar. Okay. Okay, so like we did with sampling distributions for proportions, we see certain things happen when we do a sampling distribution for a mean. So here's our population, okay, the average wait times, centered around 3, because that's the assumption, because we want a world where the average wait time is 3 days. Here's the one sample. Okay, so obviously one's below, one's above, but generally centered around 3 again. And if we did a simulation and ran several of these, it would again group around an average wait time of 3. I mean, they're not all going to be 3. There's going to be some less than 3. There's going to be some greater than 3. That's sampling variation, right? The question is, right now we're at 5.33 in our sample. Is that unusually far away? Okay, which is something we need to calculate. So under certain conditions, and we'll talk about those conditions again, a sampling distribution for a mean will be normal if a certain condition is met. The mean of the sampling distribution, or in other words, the mean of the means, will be the same as the population mean. And the standard deviation of the sampling distribution will be the population standard deviation over the square root of the sample size. So a slightly different formula. And then you see I've listed them there, what those mean. So in our sample that was taken, or the sample that they took where n was 30, let's find the standard deviation. Well, to calculate the standard deviation of the sampling distribution, the sample means, we take that out here. Oh yeah, there it is. Sorry, I should have added this. So our population mean is 3, population standard deviation is 1. Okay, you have to be given that in order to do this calculation. So the population standard deviation is 1 divided by the square root of the sample size, which will give us approximately 0.183. And what does that mean? It means sample wait times, sample mean wait times, .
typically vary by 0.183 days from the true mean wait time. There's the interpretation.
It's always the standard deviation typically varying from the mean. And we already answered this question. Yeah.
So you said sample weight times, and then you said more sample weight.
Sorry, I meant to say sample mean wait times.
Like if you didn't put mean on the test, would you think full mark or I'm just talking
I don't know if I'm doing any.
about?
Yeah. Because I mean, like if you finish the rest of it correctly, I would sort of say, is that really worth, like, it wouldn't be worth more than half mark, definitely.
Because I made them.
And I would even be asking myself, is it really critical, that word? So I'd have a tough time convincing myself of that. Sometimes word like, you know, if you missed out typically varies, yeah, I'm going to talk. Okay. Oh yeah, what if you missed the? Oh, what about if you missed from?
But you put typically, so you know what the other word is, but you're just gonna be like, I'm just thinking mark off.
But then that sample wouldn't miss. I'm not going to take a mark.
Like something writing really passionately in your truck.
Really passionately?
What do you understand? Or what do you think typically? What do you say dairy? That is moved back to the line.
Yeah, like to me, you need the word varies in there. More than you need the word typically.
I cannot believe I am having this discussion. Yeah.
What if instead of normal, you say regular?
In this world where the true average wait time is 3 days, would the sample mean we found earlier be surprising and we stand?
Yes. It would. And we do doubt the VA has met its goal. Yeah, it's goal. But we can't be absolutely sure. I shouldn't even use the word absolute. You don't really want to use absolute words in statistics.
Did you take a mark off?
Yeah,
Really?
yeah. No, I'd take 6. So free response question, you get -1 out of 5. Yeah. Just really sorry about that. Okay. Okay. Once again, we can say that the mean of the sampling distribution will be the same as the population mean as long as the sample was randomly selected. So that's really the first condition.
It's the same as when we did proportions.
So like you can see, if we've got our population, and then if we've got our sample, the simulation of several samples, and we average them out,
They're both going to be centered around 3. However, we saw and we discussed this yesterday.
if we didn't do something random, voluntary response sampling being an example of one of them, we would not get one that's centered around. Okay, we could easily get one that's, or we would likely get one that's less. Okay, so here, these two would be equal, but these two, the sampling distribution, the mean of the sampling distribution would be less. Okay. Why do you think we would assume it would be less? Why would you assume it not be greater? Think about it. It's a voluntary response. So you're contacting the clinics and you're asking them for their wait times. No, it's a voluntary response. Like let's say you send out an email to all the VA clinics in the States. And then the ones that respond, that's going to be your sample. What's that?
The people who have long wait times.
Exactly. The clinics with longer wait times, they don't want to answer. But the ones that have shorter wait times, okay, they're more than happy to answer. So we can see that's what would happen, is we'd end up with an underestimate of the actual true mean wait times. 10% condition, again, same as with proportions. Okay, so the sample size must be less than 10% of the population size. We're using mathematical notation. This. And what does it allow us to be, or what does it assure us to be true, or what does it allow us to use? It allows us to use this formula for the sample standard deviation. So those two are very similar, except instead of proportions, we're talking about means. The third condition, however, is different from proportions than it is from means. We don't use the large counts condition because you can't talk about probability of success and failure because there's no proportions to talk about. Okay? So, the sampling distribution, or sorry, the population distribution must be normal, which is kind of obvious. Like if you've got a population distribution that's normal, it's going to make sense that the sampling distribution is normal no matter what sample size you take. Okay? So if you if you are told that the population distribution is normal, then it doesn't matter what the sample size is. You can say the sampling distribution is normal. So happens for all sample sizes. But what happens if it's not normal? Well, there is a theorem in statistics that as you increase the sample size, the sampling distribution will approach normal. So you can see here, this is skewed to the right. Well, if we did samples of size 2, and we did a whole bunch of samples, all of these are samples, it's still pretty skewed to the right. If we increase the sample size to 10, less skewed, getting close to normal. If we went to 30, the sample size, it's essentially normal. So it doesn't matter if it's skewed to the right, skewed to the left, whatever. As long as the sample size is big enough, the sampling distribution will approach normal. Okay? So it will become normal
but for large sample sizes. Or for larger sample sizes. And what's the threshold?
Generally 30 for a sample size.
Okay, or the sample size is greater than or equal to 30.
And like I said, that happens no matter what the normal one looks like, or sorry, no matter what the population distribution looks like. That theorem is called the central limit theorem. Okay? Which means if your sample size is 30 or above, you don't have to worry about what your norm or your population distribution look like. Your sampling distribution will be normal. You can do normal calculations. Okay?
So when n is sufficiently large, and like I said, greater than or equal to 30, the sampling distribution for the sample mean is approximately normal.
I don't think we really need to write, I don't know why I really left that in there. I think I looked at that last year and wondered the same thing. I mean, why is it so useful? I mean, that's kind of obvious. Because if everything becomes normal with a large sample size, then we can do normal calculations. Okay, and it allows us to solve problems. That's really what it does.
So just to sum up,
Okay?
just notice I made a mistake there.
It's not large counts, it's large sample. Large counts refers to proportions. So, like we just said, we're either told that the original population distribution is normal, or by the central limit theorem, if the sample size is 30 or above, we can assume it is normal. Okay?
So it takes an approximately normal shape.
Which means we can do normal calculations. But what do we need to do normal calculations? Mean, standard deviation. Well, if it was, the sample was randomly selected, we can say that the average of the sampling distribution, or the mean of the sampling distribution, will be the same as the population mean. Okay? That's known as an unbiased center. And if the 10% condition is met, that means we can calculate the standard deviation, which is a measure of spread. So let's just revisit that question. So here's an example you would be given. I mean, this would be like a free response, okay? A full free response, where you're going to have to state conditions and do some calculations to find the probability that something happens or not. So we want to describe the sampling distribution, well, just like we did yesterday. Random condition. Well, the question said that the sample was randomly selected. %% condition. So 30 clinics were sampled. So 30 clinics, we would assume is less than 10% of all the VA clinics in the States. mean, in some states, it'd be well more than 30 clinics. Well, we have to assume that. Like, it's a pretty safe assumption. Although technically, I mean, like, if you want to be, you know, if you're going to report on it, you do need to know how many VA clinics are there in the States. Okay? But it's a pretty safe assumption that there's more than 300.
And then finally, we'll call it large counts, call it large sample. And the sample size of 30 is greater than or equal to 30. So what were all the things we could assume? We could assume that the mean of the sampling distribution will equal the population mean. The standard deviation of the sampling distribution will be the standard deviation of the population divided the square root of the sample size, and it will be normal.
You don't have to, I'm just writing these in red here. You don't, as part of your solution, you don't need to write it, but you do need to write these. Okay? Okay, so remember the sample mean wait time when the 30 clinics were averaged out was 5.33 days, which we thought seems awfully high. Well, what's the probability? Now that we've got the math, what's the probability that it would be 5.33 days or higher? So what we need to do is we need to create a sampling distribution. What was our mean? That was our mean? No. Well, no, that's the number that we got. 3. Okay, the population mean, or the mean should be 3. Then we found the standard deviation. Remember, the standard deviation from the previous page was 0.183. Okay. We got this from the previous one, it was 0.183. So that means 1, 2, 3, 1, 2, 3. So then I got to add 0.183. And then I got to add another 0.183. And then I got to add another 0.183. Go back to the mean and subtract 0.183, so I get 2.1817, 2.634, and 2.451. And remember to label. And you can just label it sample mean. Well, even before we do a calculation, if we just looked at this, where's 5.33? It's way up here. Like from here, 3 notches, I just over 3.5. How many more notches is to get up to 5.3? A lot. So 5.3 is going to be way out here. So even just by looking at the graph alone, it's like, man, that's really not going to happen, or the probability is really low. But we got to follow that up with the math. So this is where we do our normal distribution calculation. So normal CDF. So it would be like this, really. What would be the lower boundary? Because this is, we want to find the probability here, which is virtually nothing. So the lower boundary would be
If I want to find this area, the upper boundary would be
10,000.
10,000, 1,000. Either of those are fine. The mean, 3, and the standard deviation of the sampling distribution, 0.183.
So you would put that all into your calculator
And you wouldn't even get a number, you would get a number in scientific notation. Approximately 2.03 times 10 to the negative 37. So imagine writing that as a number, start here and walk the decimal point over 37 times. So you're going to have 36 zeros. That is virtually zero. Okay? So really, this is virtually zero.
What is the name of the actual 36 0 before it?
Would you take a marathon? I know.
Let's finish this off. We're almost finished it. Okay, we have to talk about the 37 zeros.
36 zeros.
So, the probability of sample mean wait times of 5.33 or more days is virtually zero. If you want to rewrite the 36 zeros after you've written it up here, knock yourself out. Okay? Obviously, this is extremely unusual. Unusual. Which suggests the VA has not met their 3-day goal.
Because we just took one sample, assuming we would get around 3 days, and we could say, yeah, they're pretty close to their goal, but we got something so extreme, no way.
Okay,